All right, so let's take a look at some of the regiochemistry of the E1 mechanism. So if we take this alkyl halide and react it with water, and let's just assume only E1 predominates, and we're not, we're just going to look at elimination. What we find is that we get a mixture of many elimination products. So let's just address how that's possible first. What we're going to do is look at the fact that, well, we got a beta hydrogen there, and then we have a beta hydrogen here. Now, that's the same as this one. Those are the same. So pulling off one is the same as pulling off the other. And so when we pull off, let's just say this one first, I'll call it A. We will get this alkene. It's also possible to get this alkene. Now, if I were to pull off beta hydrogen B, I would get this alkene. Now, there really isn't a way to control the reaction to get one of these products. So there's no way to get just one product. But the most stable product will be the major product. So if I were to ask you, first of all, to draw the possible elimination products, could you order these in terms of how much of the prevalence of them? Which one would you get the most of? Which one would you get the least of? So since we're dealing with alkenes, the first indicator of stability that you want to look at is which alkene is the most substituted or least substituted. So for this first alkene, okay, there's 3 carbons directly attached to that alkene. This one, there's 3, but this one, there's only 2. So we know that this would be the least stable product. So this one would be our minor product. It would be formed the least. Now, can you make a judgment call about the first 2? Because they both equal in substitution. They both have 3 carbons directly attached to the double bond. So since that's equal, what you want to take a look at is, well, let's look at sterics, because that's the other thing that affects the stability of alkenes. So in the first one, notice here you have 2 methyl groups cis to each other. And then I'll just draw on the hydrogen here. Here you have the ethyl cis to a hydrogen. Now let's look at the other one. On this side, you have a methyl cis to a hydrogen. And on this side, you have ethyl cis to methyl. Which one of those exhibits the least amount of steric strain? This product has less sterics because you have the biggest group here next to the smallest group. This one here, you got an ethyl that's cis to a methyl. There's a lot of sterics involved in that. And so we would say that this is the major product. And this one would be, I'll use a technical phrase here, a little less than the major product. So if I were to rank these in terms of prevalence, we'd have the most of this one and least of this one. And the second one would be somewhere in between. Again, it's not your job. I'm never going to make you try to figure out, well, what's the percentages of them? The only way you figure that out is to go in the lab and do it. And so that's not my goal for you to do this in class. My goal is for you to just be able to rank them in terms of their prevalence. All right, now let's talk about the stereochemistry of SN1. Again, let's review. So recall that SN2 results in inversion of configuration. So if the reaction happens at a chiral center, since the nucleophile has to attack from the opposite direction, it will have the opposite stereochemistry as the original leaving group. Now, that's for a concerted mechanism. Remember, SN1 is stepwise. Since SN1 involves a carbocation, it's going to change the game a little bit. Let's think about a carbocation. So let's just draw a basic tertiary carbocation here. What is the hybridization of the carbon with the positive charge? Well, we talked about this before, it's sp2. So if it's sp2, what is its shape? Trigonal planar. And I'm underlining that word planar because I want you to think of this as a flat intermediate. And where is that positive charge? Positive charge is the empty p orbital. That p orbital is perpendicular to all of the other atoms attached to that carbocation. So how does this affect stereochemistry? Let's take a look at this reaction here. First step, leaving group leaves. And that creates a trigonal planar intermediate. This is kind of rotated to imply that all of these atoms here are in the same plane. It's flat. So now in comes our nucleophile. And the nucleophile has a choice because it could bond with that empty p orbital going from that direction, or it can bond with that empty p orbital coming from that direction. And in reality, you can't tell that nucleophile, oh, I want you to only come from one direction. I really just want one stereoisomer. You can't do that. The nucleophile attacks that p orbital based purely on statistics. Half of the time, it comes from one direction, and half the time, it comes from another direction. So what does that mean in terms of products? Well, in some, you'll have the nucleophile going this way, and some, you'll have the nucleophile going the other way. And you have 50% of one, 50% of the other. Now, I know I'm kind of going back to almost the beginning of the semester, but what do those two compounds look like in relationship to each other? They're enantiomers. And what do we call an exact 50-50 mixture of enantiomers? It's a racemic mixture. So an SN1 reaction on a chiral center leads to what is called racemization. That's just a fancy term for saying it makes a racemic mixture. We're taking something that's enantiopure. This is 100% of one enantiomer, and we're creating a racemic mixture out of it. So let's do an example. Now, all we're going to do is draw the result of an SN1 reaction. Not going to worry about elimination right now. Okay, so first things first is you should always pay attention if the leaving group is at a chiral center. If it's not at a chiral center, then you don't care about stereochemistry because stereochemistry doesn't exist. But since that is occurring at a chiral center, I know that in some of my products, this methyl group will be going back, the nucleophile would be coming out at you, and in some of the product, the methyl group is now coming at you, and the nucleophile would be going away from you. And since you have exactly 50% of one, 50% of the other, we would call that a racemic mixture. Now, the last thing we're going to look at is how do we know that there are two different elimination mechanisms? So we're kind of going away from theory and going into actual real world evidence that we have two different mechanisms, E1 and E2. So what scientists used is something called the kinetic isotope effect. So the name kind of describes what they're doing. So kinetic, we're looking at rates. So kinetic deals with looking at two reactions and see if their rates are different. An isotope, in this case, we're looking at a different isotope of hydrogen. So recall from general chemistry, hydrogen exists as protons, 1H, most of them, but there are a small percentage of hydrogens that exist as deuterium, or 2H. And so what scientists do is they perform two similar reactions, but instead of pulling off a regular hydrogen, they'll use the same substrate, but all of the hydrogens are deuterium. And they basically ask themselves, do these reactions have different rates? And the theory behind this is that a carbon deuterium bond is a stronger bond. We're not going to go into why that is, but that's scientific fact. Carbon deuterium is a stronger bond than a carbon hydrogen bond. So if breaking the carbon hydrogen or carbon deuterium bond is in the rate determining step, then the difference in rates should be large. And when I say difference, we're comparing the ratio of the rates. Now, here's how scientists figured this out. If we compare what E1 looks like. So in E1, the rate determining step involved forming a carbocation. And then the base would pull off the hydrogen after that. So we have a rate determining step. Now, if we pulled off a deuterium, that should be a carbocation. What scientists noted is that in an E1, the ratio of the rates was almost 1. That means there was no difference in pulling off a hydrogen versus a deuterium. So they noticed that the rate determining step doesn't involve removing a hydrogen or deuterium. But for an E2, which was a concerted mechanism, this rate determining step does involve pulling off a hydrogen. And what they found in the case of E2, the ratio of the rates is large, like between 6 to 8 times more. So pulling off a hydrogen was like 6 to 8 times faster than pulling off a deuterium. And that means the rate determining step involves removing a hydrogen or a deuterium. Because there was a change in rate based off of pulling off that hydrogen or pulling off that deuterium, that means the rate determining step involved breaking that bond. And so this is how chemists discovered that there were two different mechanisms, because sometimes the rate was not different if a hydrogen was replaced by deuterium, and sometimes the rate was drastically different.